Class B power amplifier is basically consisting of two transistors, right? One transistor will work for positive half cycle of the input, say transistor Q1, and the second transistor, that is Q2, works for the negative half cycle of the input. Okay, so at any given point of time, only one transistor is under operation. Okay, but by doing so, what we can do is we can produce a full cycle output. Okay, so V01 is the output given by the transistor Q1, and V02 is the output given by the transistor Q2. Okay, so across the load RL, the voltage which is available will be of 360 degree duration. All right, and I had also drawn the equivalent circuits for the two transistors. Okay, so this is for the transistor Q1, which is under operation, and the second equivalent circuit is for transistor Q2, which is under operation during negative half cycle of the input. Okay, so today what I will do is I will draw certain waveforms. Okay, so before drawing the waveform, okay, let me define few waveforms here. Okay. So let us say let IS is equal to source current. Okay, and let us define IB1 is equal to base current of Q1. In short, let me write, and IB2 is equal to base current of Q2. Okay, the respective base currents. And then we have IC1, the load current. Okay, IC1 is equal to collector current of transistor 1, and IC2 is equal to collector current of transistor Q2. Okay, and then we have the load current. Okay, so let's say IL is equal to the load current. Load current of class B power amplifier. All right. Sorry. So that is about the definition of different currents. Okay, now let us try to plot the waveform. Okay, so first let us plot the source current waveform. Okay, so I need to draw certain guidelines. Let me slightly minimize. Okay. Say source current axis, and then we have base current IB1, and separate axis is required for base current 2. Okay. So this is the time axis for source current, then base current, and then base current 2. Similarly, IC1 and IC2 I need to draw. Say this is for IC1, and the other for say IC2. Okay, and then finally we have our load current. All right, load current. let's say here. Fine. So let me mark the x-axis. X-axis is going to be the time axis. Okay, and then we have the y-axis. We have multiple signals along y-axis. So initially, let me start with the source signal. Okay, and then let me draw the base current 1, IB1, followed by IB2, and then IC1, then IC2, and finally the load current IL. Okay, let me see whether I have marked source current in our main circuit. If I haven't, let me mark it now. All right, so this is my source current, right? This is my source signal VI, so this will be the source current IS. Okay, so IB1 and IB2 I have already marked, and okay, let me mark the collector current also, because collector current I1 is nothing but IC1. Nevertheless, let me mark this as IC1, the RMS value. Okay, similarly, let me mark the lower collector current as IC2. So capital IC2 simply refers to the RMS value. Okay, you shouldn't be get confused with that. All right, fine. So let me plot the source current. So source current going to be a complete 360-degree bidirectional signal. All right. So let me draw first the source current signal. A 2-cycle should be fine, I think. Okay. Once I draw the source current signal, what I can do is I can draw the guidelines. All right. So let me draw the guidelines. Let's say a blue color. Okay, these are all thin lines. Okay, these are all thin lines meant for sketching the waveform. Okay, all right. Now we have the sketching of the respective base current. All right. So in case of transistor Q1, the base current IB1 persists for only 180-degree duration, right? And that too, it persists for 0 to 180-degree duration. That means to say, at IB1, you are going to have basically the time duration 0 to 180 degree. Okay, so that is the positive half cycle. So let me sketch IB1. Okay, so positive half cycle you are going to have. Okay, and the negative half cycle basically makes the transistor Q1 to get into turn off mode. Okay, so I have to draw the negative half cycle as well. Okay, that's because the signal is present for 360-degree duration, but the conduction is present for only 180-degree duration. Okay, so that is for IB1. And IB2, how are you going to draw? So IB2 can be drawn with a complementary level, right? Because you know that potential at A and potential at B are kind of antiphase in nature, right? So that's the reason, you know, your IB2 going to be a phase inverted signal. So for the positive half cycle of IB1, you're going to have a negative half cycle. So that's your negative half cycle, followed by positive, and then negative half, and then positive half. Okay. So let me shade the region of IB2. Okay. So this basically shading simply refers to conduction duration, conduction cycle, I can say. Okay, this shading simply refers to conduction cycle. All right. All right. So when current IB1 flows for 0 to 180 degree duration, transistor Q1 is triggered. Triggered means it is turned on. Hence, there will be a flow of collector current. Okay. So the collector current IC1 flows for the positive half cycle of IB1. So this is your collector current. Okay. And what about IC2? Can anyone tell? I mean, sorry, for the negative half cycle, what happens? Can anyone tell me quickly? Will there be any collector current pulse? There won't be any collector current pulse. That's because transistor cannot work for negative voltage level. Okay, because we are choosing NPN transistor. So NPN transistor cannot work for negative voltage level. Hence, the negative half cycle is clipped. Okay. The transistor Q1 again, comes into picture for the next positive half cycle. So for the next positive half cycle, transistor Q1 again conducts, and hence there will be a flow of collector current IC1. Okay, so that's the wave nature of IC1. IC2, what happens to IC2? Okay, so IC2 is the collector current of transistor Q2. So IC2 flows for 180 degree to 360 degree duration. Okay, that means to say during 180 degree to 360 degree duration. Okay, so let me mark. So that is here. This is your 360 degree. Okay, so between 180 and 360, basically IB2 is kind of positive bound, right? So your base current is positive bound. That is because the input transformer what you have used is basically providing you a phase inverted output. So transistor Q2 stays off for 0 to 180 degree duration, because for 0 to 180 degree duration, the base current is negative bound. Okay, so whenever the base current is negative bound, the NPN transistor stays in off mode. Okay. So let me use blue color over here. It's slightly thicker. So off. So transistor doesn't work for 0 to 180 duration. And when the base current is positive going, okay, so base current is positive going for 180 degree to 360 degree duration, the transistor Q2 conducts, and hence there will be a flow of collector current. Okay, so let me mark this with the blue color. Okay, and once again the transistor gets into non-conducting zone for the next half cycle. Okay, that is between 360 degree to I think it is about Yeah, 540. Okay. And once again, the transistor comes into conduction for the next half cycle. Okay. So basically what is happening is, the two transistors are working in the alternate half cycles. Okay. When IC1 is present, IC2 is off. And when IC2 is present, IC1 is off. Okay. By doing so, there will be a complete 360-degree cycle available at the load. A full cycle available at the load. Okay. So this is the wave nature of class B power amplifier. Okay. Any doubts? You can ask me. Okay. Any doubts?
No, sir.
All right. Fine then. So that's about the waveform sketching of class B power amplifier. Okay. Now let us look into the analysis part. Okay. So let me write the analysis. Okay. Once again, as you know that your power amplifier is consisting of uh, DC signals as well as AC signals. You have to break your analysis into two types: DC analysis and AC analysis. So first, let me write DC operation. DC operation. All right. Now, in case of DC operation, okay, you know that uh, the transistor Q point is located on x-axis. Okay, the transistor Q point is located on x-axis. Therefore, coordinates of Q point are x comma y, right? So that is equal to Q of what is x? X is VCQ. And what is y? Y is 0. Okay, that's because the Q point is sitting right on the x-axis. So you will have x coordinate, but your y coordinate going to be the origin point, and origin is 0. So you have only voltage present over there. Okay, and you know that VCQ is equal to power supply voltage. That is the maximum power supply voltage. Okay, so that's about your Q point. Okay, once you know the Q point, what you can do is you can quickly draw the load line. Okay, so let me draw the load line. Okay. So this is your IC and this is your VCE. So first let me mark the DC load line. So DC load line going to be a straight line because you have a transformer, and transformer resistance is very, very small. Okay, that's the reason you will get a straight line. Okay, so this is your DC load line. DC load line, and this is the location of Q point. Okay, let us mark. It is VCC comma 0. Okay, because I have already told you the VCQ value itself is VCC. Okay, so that's your DC load line. Okay, now AC load line you will draw in such a way that, okay, let me write down AC load line. Drawn in such a way that the line passes through the Q point with a slope equal to minus 1 by RL dash. It is similar to your transformer coupled class A power amplifier. Okay, so where RL dash is delta Y by delta X. So based on your load resistance, you have to select delta Y and delta X. So delta Y is delta IC and delta X is delta VC. So based on that, you can decide the shape of the line. Okay, so this is how it is going to look like. Okay. So the line is passing through Q, and the slope of this particular line, is minus 1 by RL dash. So this is AC load line. Where M is equal to minus 1 by RL dash. All right, done. Now, once this is done, what you can do is you can select equidistant points. Okay, so this is the Q point. So what you do, one point you take it above the Q point, let's say here, and the second point you take it at an equidistance, okay, but below the Q point. Okay, and then you draw the guidelines. Okay, so let me draw a guideline from this point. Then let me also draw the guideline from the x-axis. And the third guideline is drawn from the bottom point. Okay, that's somewhere over here. Okay. All right. So once you have the guidelines, you can plot the collector current waveform. Okay. So just observe how am I going to draw. Now, this is your origin. Okay. So I'll mark the origin with a point O. Now, from the Q point, okay, or rather I can put it in this way. The region above the Q point is positive bound, right? Because the region above the Q point, okay, basically gives the positive going signal, and hence, you will have the flow of collector current for that particular region. Okay. So the collector current flows only for positive half cycle of the input. Okay. On the other hand, the negative half cycle, what happens to negative half cycle? In the negative half cycle, you can see that the region is found below the reference. So below the reference, there won't be any conduction happening in case of an NPN transistor. So what happens is that during negative half cycle, the transistor stays off. Okay, this is off. Okay, and this zone is on zone. Okay, and this is your I maximum value. Okay, or in short, you can write this distance, okay, as IM, the maximum value. Okay, so only 180-degree pulse exists for class B operation. Similarly, the output you can draw. Okay, so let me draw the freehand guidelines here. Okay, so output is existing only for half cycle basically. Okay, so something like this you can draw. Okay. So that's your positive pulse, and your negative pulse, sorry, I mean this is the negative pulse of the output, and the positive pulse is missing. That's the reason I have drawn it in dotted lines. All right, so this is my output voltage, and this value is basically V minimum value. And if you were to measure this particular value, from this line to this line, okay, you will get the value as Vm. Okay, Vm. So the maximum value of current signal is Im, and the maximum value of voltage signal is Vm. All right, fine. So that's your current and voltage signals respectively. Okay. Where you can also write expression for RL dash, where RL dash is equal to Vm by Im. RL dash is equal to Vm by Im. So for DC operation, let us first write down the expression for DC power input. Okay. So let me write expression for PI DC. Okay. Now, PI DC cannot be simply taken as ICQ. Okay, why you cannot take it as ICQ? Can anyone tell me? You cannot take it as ICQ because if you look at the coordinates of Q point, ICQ value itself is 0. That doesn't mean that the output is 0. The output exists, right? You can see that the output exists for a complete 360-degree cycle. That is due to the alternate conduction of the two transistors. Q1 conducts for 0 to 180 degree and Q2 conducts for 180 degree to 360 degree. So in case of class B power amplifier, the value of load current is derived from the two collector currents, because when there is collector signal, okay, say for example, when there is collector signal IC1, there will be positive pulse of output voltage. Similarly, when there is collector signal between the interval 180 degree to 360 degree, there will be a negative pulse of load voltage. Okay, so that means to say the two collector currents basically, constitutes the load current, and hence in order to write an expression for the load current, basically you have to consider the concept of the RMS values of the two collector currents, or the DC values of two collector currents. So in order to write down an expression for DC power input, okay, let us consider the DC value of IC1. Similarly, let us also consider DC value of IC2. Okay.
We had drawn a couple of waveforms also over there. Okay. So source current waveform, then base current waveform. Okay. Just to clarify, what happens is that Q point is the current waveform, then base current waveform. Okay. Just to quickly brush up. In class B power amplifier, what happens is that Q point is set at in the cutoff region, due to which transistor conducts only for 180 degree duration. But you want your output to be 360 degree one. That's the reason what we do is we take two transistors. One transistor conducts for positive half cycle, and the other transistor conducts for the negative half cycle. So the conduction is dictated by basically the primary transformer, right? The primary transformer gives a secondary output, which is a phase opposed one, in the sense if voltage at node A is positive going, the voltage at node B will be negative going. So the NPN transistors are they will conduct only for a positive going signal. That's the reason what happens is that whenever there is positive going signal, the transistor gets into conduction. Okay, so that was the whole working of a class B operation. Okay, and therefore, when transistor Q1 starts to conduct, we get a collector waveform for 0 to 180-degree duration. And when the transistor Q2 gets into conduction, we get a collector waveform from 180 degree to 360 degree. That means to say each transistor conducts for 180-degree duration only. But the load current which is flowing through the load will be a 360-degree one. Okay. Now, in order to write an expression for power, okay, we have to find the power input, that is DC power, and we also need to find out power delivered to the load, which is the AC power. Okay. Now there is slight problem while finding out DC power. That's because in class A operation we used to consider power input, that is PDC, as VCC into ICQ. But in class B operation, you cannot take ICQ. That's because, see, the Q point, okay, the value of current at the Q point is 0 ampere. So you cannot take ICQ. Instead, you need to use the waveform. Okay. So you know that the collector waveform exists for 180-degree duration. That means to say, each of the collector waveform takes the shape of a half rectified waveform, right? Signal is present for one half cycle, and then the signal is absent for the other half cycle. So IC1 and IC2, you know, they resemble the half wave rectifier waveform. So that's the reason what we have to do is while calculating the power input, that is the DC power input, you have to consider the DC value of IC1 and IC2. Now, DC value of IC1 is a half wave rectified waveform, right? So the DC value is Im by pi. Similarly, the DC value of IC2 going to be a half wave rectified waveform's DC value. So that is again Im by pi. So while writing down an expression for DC input, you can see that Pi DC is equal to voltage into current. DC voltage into DC current. So what is that total DC current? The total DC current is comprising of IDC1, okay, of IC1 and IDC2 of IC2. So there is an addition of 2 DC current. So that gives 2 Im by pi. So Pi DC is VCC into 2 Im by pi. So that's your expression for input. Okay. Now for AC operation, of course, you can first define what is RL dash. RL dash is RL by K square, where K is N2 by N1, the transformation ratio. Okay. And AC power, you can find something like the product of VRMS into IRMS. So that's what I have written, VRMS into IRMS. So what is VRMS? Maximum by root 2. IRMS is maximum by root 2. So it is VMIM divided by 2. Therefore, the conversion efficiency eta is equal to output by input. So output by input, that is P naught AC by Pi DC. So what is P naught AC? VM Im divided by 2. That's here. Divided by Pi DC. Where is Pi DC? We had written an expression, right, for Pi DC. That's 2 Im by pi into VCC. So that's over here. Okay. So simplify further. You can see that Im gets cancelled. And anyhow, this 2 will come to the denominator, and therefore you will have your efficiency expression as pi by 4 into Vm divided by VCC. Okay, so this is the expression for class B operation. And remember, this particular expression holds good for both the types of class B power amplifier circuits, that is push-pull power amplifier as well as complementary symmetry power amplifier circuit. All right, fine. So having found the maximum efficiency, you can find, having found the expression for conversion efficiency, you can find the expression for maximum efficiency. All right. So maximum efficiency, what we do is we consider first the load line. Okay. So I have redrawn the same load line which I had drawn earlier. Okay. And while calculating the maximum efficiency, what we are basically trying to do is we are trying to allow the maximum flow of current as well as voltage. Okay. So I mean, under normal circumstances, this would have been the white colored waveform. Okay, this would have been your output waveform. Okay, but you can see that this output waveform is has not reached to its full limit, right? Your output waveform is being limited to this particular region itself. But in maximum efficiency, what we are trying to do is that we are trying to allow the maximum output voltage to occur across the load terminals. All right. So the orange color waveform basically talks about the maximum output voltage that may be present across the load terminals. All right. So taking that into consideration, we can say that the maximum value, okay, so of course V minimum is 0, but the distance measured from origin till the Q point is VCC, and that itself is the maximum value. So therefore, eta max will be pi by 4 into Vm, right? So what is Vm? At maximum efficiency, your Vm is equal to VCC. So you are going to write VCC in the numerator. So numerator and denominator VCC terms are going to get cancelled out. Hence, you are left with pi by 4 into 100. So if you put it in your calculator, pi by 4 turns out to be 78.5. Okay, so the maximum possible conversion efficiency going to be 78.5%. All right, so that's your maximum conversion efficiency. Very, very important. All right, this is very, very important. Okay, and yeah, here I have written a note mentioning that this particular derivation holds good for both the types of transistors. Okay, that is push-pull class B power amplifier or complementary symmetry class B power amplifier. All right, fine. So that's about the efficiency calculation of push-pull power amplifier as well as complementary symmetry power amplifier. Okay, now let us talk about the power dissipation. Okay, so what is the general expression for power dissipation? Power dissipation is nothing but the waste power, right? The power which is not being utilized in the conversion process. So how will you find out? Simple technique is to subtract the input from the output, okay, or rather subtract the output from the input, right? So PD is equal to PIDC minus P naught AC. So PIDC I know 2 by pi IM into VCC. And P naught AC I know VMIM divided by 2. Okay, all expressions being given, okay, previously. Okay, see PIDC 2 IM by pi into VCC. Okay, and P naught AC IM VM divided by 2. Everything is given. Okay, I have to just substitute. So therefore, PD is equal to input minus output, or PD is equal to, let me start subtracting. Okay, so 2 by pi into VCC. Okay, IM, what I'm going to do in place of IM, I'm going to write VM by R. That is V by I ratio I'm going to write. Similarly, I'm going to do the same thing to the second term. Okay, fine. So to find an expression for maximum power dissipation, what you have to do is you have to apply the principle of Maxima theorem. So Maxima theorem says if you differentiate PD with respect to the variable factor Vm, and if you equate it to 0, you'll get a condition for maximum power. So basically, we are trying to differentiate PD with respect to Vm and equating it to 0. So when you differentiate, you will get this kind, right? So PD with respect to Vm, so this Vm going to get cancelled. So it is 2 by pi into VCC into 1 by RL dash minus differentiation of second term. So it is 2Vm divided by 2 RL dash, 2 gets cancelled. And this is what you get it in the end. So Vm is equal to 2 by pi VCC is the condition for maximum power dissipation. Okay, condition for PD max. All right, fine. So next up, what we have is power rating of transistor. So why I'm discussing all this, because in problems they will ask, calculate the power rating of each transistor, etc., etc. So that's the reason I'm giving you the formulas beforehand, right? Okay. So power rating of transistor. Okay. So to find power rating of transistor, what we will do is we will first write down the AC power expression. So PAC, okay, is equal to Vm square divided by 2RL dash. Okay. If you haven't understood, can give you the reason also for writing down this expression. So PAC is equal to Vm Im divided by 2, right? So you substitute Im as Vm by RL dash. So what do you get? You get Vm into Vm, that's Vm square divided by 2 RL dash. Okay, that's the reason I have written this expression. Okay, and we also know that Vm is equal to VCC for maximum efficiency. Okay, so therefore PAC maximum. What could be the maximum power delivered to the load? So maximum power delivered to the load takes place when your maximum value of the AC output is equal to the VCC value. So PAC maximum is equal to, in place of Vm, you substitute VCC. So that's going to be VCC square divided by 2RL dash. All right. So we'll keep it as equation 1. Okay. Now let's take up PD maximum. PD maximum. So what is PD maximum? So for PD maximum, okay, what you can do is you can substitute this particular expression for PD maximum. This particular expression you can substitute. Okay, so let me write for now for PD maximum. Okay, use Vm is equal to 2 by pi VCC. Right? We have already derived this particular expression. So when we use that particular expression, we get PD maximum is equal to 2 into, okay, in place of, yeah, so it is 2 by pi square into VCC square divided by RL. Okay, so that is equal to, you can take out this term outside so that you will get a previously known result. VCC square, I'll divide by 2. Okay, so 2 goes 2 times in 4, so basically you will get the same expression, RL dash. Okay, now by modifying this expression, what I get is this second term, okay, that is VCC square by 2RL dash is basically equation 1. So that is 4 by pi square, okay, into P naught AC maximum. P naught AC maximum. So that's the expression for maximum power dissipation. Okay, maximum power dissipation. Okay. Okay. So therefore, power dissipation per transistor is equal to basically it is PD max divided by 2. So power dissipation per transistor is equal to PD max divided by 2. Okay, the reason being 2 transistors are used. Unlike in class A only 1 transistor is used, but in class B 2 transistors are used. So each transistor dissipate a power of PD maximum divided by 2. Okay, so that is your expression. Okay. All right. So now let us look at the second type of class B power amplifier circuit, which is called as complementary symmetry. Okay. Now, some salient features of complementary symmetry class B power amplifier compared to the push-pull power amplifier is that the first noticeable feature is that uses dissimilar transistor. It uses dissimilar transistor, that is NPN and PNP. Okay, so that's the first and noticeable difference from the previous one. And the second major difference is that no transformers are used. No transformers are used. Okay. And yeah, so these are the unique features of class B power amplifier. Okay, now the question is no transformers, right? No transformers. Therefore, how to achieve impedance matching? Okay, how to achieve impedance matching? See, transformers are introduced to improve impedance matching, but we are saying that in complementary symmetry class B amplifier, we are not going to use a transformer. Then how are we going to get the impedance matching? Okay, so that is possible. That is possible by driving the transistor pair, because there are 2 transistors, right? So impedance matching is possible by driving the transistors in emitter follower way. So driving the transistors in emitter follower way, it is possible to achieve impedance matching. All right, so this is the main feature of complementary symmetry class B power amplifier. Okay, now let us look at the circuit diagram. Let me draw the circuit diagram. Okay. So this is the main circuit. The first transistor, okay, let me consider it as NPN transistor, say transistor Q1. Okay. So the emitter of first transistor is connected to the emitter of second transistor. Okay. But the second transistor is a PNP transistor. You can see outward emitter terminal for Q1 and inward emitter terminal for Q2. Okay. So collector of first transistor is driven by positive DC supply, and the collector of second transistor is driven by negative DC supply. Okay, that means to say this collector is at higher potential, and this collector will be more negative, or it is at the lower potential. Okay. Now, the two bases, okay, are connected to the input. Okay, so each of these two base terminals, is connected with a coupling capacitor to avoid the DC that may flow into the system. And these two are connected together, and it is given to an incoming AC signal. So this is your input. It's a bidirectional signal. Okay. And as I was mentioning, this is basically an emitter follower circuit. That's the reason the output is tapped from the emitter. Okay, so we tap our output from the emitter. Okay, something like this, and this is then given to the load, which is represented by RL. Okay, and the load voltage is measured with respect to ground. Okay, so this is your push-pull symmetry class B power amplifier circuit. Now you can observe that there is no transformer on the input side and there's no transformer on the output side. So since there is no transformer, what happens is that, let's say your input is of this kind. Okay, let's say your input is of this kind. So the input which is being fed to the first transistor's base going to be something like this. Okay. And similarly, the input which is getting applied to the base of the second transistor will also be the same type. Okay. That's because there is no phase splitting transformers is used. So identical input being fed to the first transistor base as well as the second transistor base. But how the operation takes place. Okay, so let us look at the operation. Okay, operation is very simple. So first let us consider during the positive half cycle of the input. So let us divide our working into two zones. What happens during positive half cycle of the input and what happens during negative half cycle of the input. All right, so during positive half cycle of the input, let me color it with white. Okay, so the input is positive going. So each of the transistor base, receives a positive pulse at the input. Okay. Now, can anyone tell me which transistor conducts? Can anyone tell me for this particular circuit logic, which transistor conducts? You decided to keep quiet, or probably someone in the class must have asked you to keep quiet. Okay, that's not good. You are not learning, that's fine. You cannot block others from learning. Okay, unity is there. Unity should be used for a good cause, not for this. Okay, you will turn out to be a very bad engineers in the end if you don't participate in classroom discussion. All right, since you are not interested to answer, I have no other clue. So during positive half cycle of the input, transistor Q1 conducts. That's because transistor Q1 is an NPN transistor, and NPN transistors works for positive voltage levels. All right. So PNP cannot handle positive going signal because PNP works for negative going signal. So during positive half cycle of the input, Q1 conducts and Q2 stays off. Okay, due to which the equivalent circuit looks something like this. Let me draw the equivalent circuit. So this is my input. This is Rn plus minus. This is your V0. Okay, so I'll write Q2 is off, and let me write it in a, keep it in a circle. So only Q1 is on. So you can see that this is how the current is going to flow. Okay, so that's your output. So your output, let's say V01, will have a positive pulse. Okay, so that's for positive half cycle. Now let us consider the case of a negative half cycle. Okay, so during the negative half cycle of the input, during the negative half cycle of the input. So for negative half cycle, what I will do, let me use blue color. Okay, let me use blue color. Okay. So my input is negative going. That means to say I'm considering negative half cycle of the input. So when you couple a negative half cycle of the input to each of the base terminals, okay, each of the base will be receiving a negative half cycle here. Okay. Now the question is, which transistor conducts? Okay, since you haven't answered, I'm going to answer. Since you are giving a negative pulse to the transistor bases, transistor Q2 is going to conduct, because the negative pulse, activates only PNP transistor. Okay, NPN transistor will not be activated because NPN transistor anticipates a positive going signal. So for negative half cycle, PNP, and for positive half cycle, NPN. So in alternate half cycles, the two transistors are going to come into picture. So during negative half cycle, let me write Q2 conducts, since PNP transistor works for negative half cycle. Q1 doesn't conduct. Okay, Q1 doesn't conduct. Okay, so here also I will write Q1 conducts because NPN works for positive half cycle. Okay, positive half cycle. So if Q1 doesn't conduct, what will be the the state of the circuit? Okay, let me redraw the equivalent circuit. Okay, the lower half I'm going to consider because upper half is basically inactive, right? So that's my emitter terminal, and this is my collector terminal, which is maintained at negative potential, okay, or minus VCC, because it needs negative DC power supply. And this is where my resistor, load resistor, is connected. Okay, so that's my ground, and this is my RM. Okay, and this is how the current will flow. The emitter current you can make out, right? In one. Okay, so you can see that the current is reversed, right? So that's the reason your V0 polarity, if you look at carefully, the current is entering from the bottom side, right? So this is positive and this is negative. That means to say the V02 going to be a negative voltage. Okay, so what I will do, I will shade it with this. I will shade it with this because the blue color I have used to show the negative cycle phenomena. Okay, so this is the equivalent circuit. So Q2 is under operation, Q1 is off. Q1 is off. All right, so that's the operation of class B complementary symmetry transistors. Okay. Now here, let me write a note that same waveforms of class B push-pull operation push-pull operation is used in complementary symmetry circuit as well. Okay, so the same waveforms, you just copy and paste it over here. I don't think that you may do it. So what I will do. Okay, so I have just copy pasted. That also you may not do it, so I have done it. All right. So that's about the operation, and the same thing. You can see that. See, look at the voltage, positive pulse and negative pulse. Okay, so basically you will have a rectified collector waveform. Okay, so that completes your class B operation. But there's a small phenomenon that needs to be understood well in class B operation, and that too it creeps in case of complementary symmetry transistor. Okay, so that phenomenon is called as crossover distortion. In class B operation. So far we didn't discuss about it because in operation we cannot bring this concept because the analysis becomes difficult. That's the reason separately this particular concept is being dealt with. Okay, this is called as crossover distortion. Now, what is crossover? Now, the meaning of crossover is zero crossover of input signal. The meaning of crossover, a broad meaning of crossover is that the zero crossover of the input signal. That means to say, whenever the input signal is crossing the zero value, the output will have some kind of distortion. Okay, so let us dig deep into this. Okay, fine. So first let me draw the input. Say this is Vi and say this is T. This is V0 and this is T. So first let us draw the input. Okay. Now let us mark the two threshold levels of transistor. Okay. So basically this is for complementary symmetry. Okay, this comes in complementary symmetry transistor. Two threshold levels. Two threshold levels as in one threshold level is set by NPN transistor and the second threshold level is set by PNP transistor. So let's say this is the threshold level for NPN. And this is the threshold level for PNP. PNP. Okay. So this refers to VB is equal to 0.7 volt, and this blue line refers to VB is equal to minus 0.7 volts. Okay. So first you mark the threshold level. So this is for PNP, and this is for NPN, right? Because there are two dissimilar transistors being used over there. Now let us plot the output. In order to plot the output, you have to draw the transition points. So you get a transition point here, and then at 0 crossover, and then at minus 0.7 volt level. Similarly, you get 3 transition points near to each half cycle. Okay. Now what you do, you draw the guidelines from these transition points. Just zoom it a bit. Okay. The second guideline and the third guideline. Okay. Similarly, you need to do the same thing near the other places as well. So here also you'll get it. And then at the middle, then at the third point. So these guidelines will help you in sketching the waveform basically. Okay. That's the reason I'm drawing it in thin lines, because they're not the part of actual waveform. All right. So now that you have drawn the guidelines, okay, you will be able to sketch the waveform. Okay. Now the concept of threshold voltage is something like this. Clipper circuits you have studied, right? In case of clipper circuits, the clipping used to take place at VB level or at the desired reference voltage level. The same thing is going to happen over here. Okay. Now here what is happening is, as long as your input, okay, I'm talking about the positive half cycle. I'm talking about the positive half cycle. As long as your input is less than VBE, okay, let's say VBE1 and let's say this is VBE2. As long as your input is less than VBE1, the transistor is in off state. Okay, so off state in the sense, okay, there's one more guide point right here. Off state in the sense, till this point, the transistor doesn't conduct. So transistor remains off. Okay. Once your input signal starts to rise above VB, the transistor is going to conduct. So the transistor is going to conduct from point A to point B. Okay. So this is your point B. So this is A and this is B. So transistor will conduct here. Done. Now again, from point B to point C, you see that your input is less than VB1. Therefore, the transistor stays in cutoff region. Hence, there is no conduction. Similarly, during negative half cycle, the same phenomenon comes into picture, but it appears in an inverted manner because you're talking about the negative voltage. So during negative half cycle, when your input is less than the threshold value, the transistor is in off state. Okay, that is from point C to D. So this is B, C, and D. Once your input starts to exceed the VBE2 value, that is from point D to E, what happens? The conduction of transistor Q2 takes place. There will be a negative pulse. And similarly, between the interval E to F, the input is less than VBE2, hence the transistor gets into off state. And in the next positive half cycle, when your input is less than VBE1, the transistor again gets into off mode. So basically what is happening is that there is a discontinuity at zero crossover of the input. And this particular distortion is called as the crossover distortion. Okay, that's because the distortion is taking place. The distortion is taking place nearer to the crossover of the input signal, and that's the reason it is called as crossover distortion. So your actual output waveform will not be a pure sinusoidal waveform in case of class B complementary symmetry operation. Instead, it will have a distortion of this kind. Okay, and this distortion is called as crossover distortion. Crossover distortion. Okay, so this is one of the drawback of complementary symmetry class B power amplifier. Okay, though you are not using transformer, so by not using the transformer, you can achieve so many things. You can achieve lighter circuit weight. You can make it very compact. You can make it cost effective. You can improve the frequency response because transformer is noisy. But at what cost? At the cost of crossover distortion. Okay.